The local extrema of a function of two variables, that is the place where you locally have maximum or you locally have minimum. Not necessarily the biggest the function ever is, or the smallest it ever is, but the biggest in a neighborhood or smallest. Okay, local extrema covers both the local maximum and local minimum. Alright, so local extrema occur at solutions to the system of equations. The partial derivative with respect to x of f is 0 and the partial derivative with respect to y of f is equal to 0. That's a system of two equations. Okay, actually calculating the derivatives gives me an equivalent system of equations. Let's see, the derivative with respect to x of this is 2x. And derivative with respect to x of the second term is y. And then the derivative with respect to x of y squared is nothing. Looks like I also have a plus 3 for that term and nothing else, so that equal to 0 is the first equation. And the second equation is the derivative with respect to y of that. I will get an x, a 2y, and a negative 3. Now, that's a system of equations that I can't immediately see a solution to, so I want to simplify it to a system of equations that looks a little bit easier. Now, there's a whole bunch of methods you might have been taught to do this, like rearranging the first equation with y on one side and x on the other, and then substituting one side of that equation into this. That's good. I would like to make a hint at something that you'll be doing much more often later, and it's just a lovely way of thinking. I am going to recognize that in the first equation I have 1 times y, while in the second equation I have 2 times y. And I would like to have 2 times y in both equations for a particular reason. So I'm going to multiply the first expression here by 2 to give me 4x plus 2y. And I'll move that 3 to the other side and also multiply it by 2 to get negative 6. And then I will leave the second equation as is. The idea here is, oh no, actually I'm moving the 3 to the other side. I have multiplied the first equation in a sense by 2, both sides of this equation by 2, and rearranged a little bit, and done nothing to the second equation except for move that 3. Because I did that because now I have a 2y here and a 2y here, and then I can do kind of arithmetic of equations. I can subtract the second equation from the first, if you like. And when I do that, 4x minus one of the x's, that's 3x. And 2y's minus 2y's is 0 y's. And so I have eliminated y from the first equation. And while that tells me that x is negative 3, I'm going to continue to write this equation this way because now I'm going to well, in the same step, would you let me multiply this equation by 3? So I get 3x plus 6y is equal to 9. Okay, the reason I did that is much like the reason I multiplied this equation by 2 is because I had a coefficient of 3 on x in my first equation. If I had a coefficient of 3 of x on the second equation, then I could perform this arithmetic of equations again, and that would allow me to eliminate x from the second equation. So that is, I am going to replace the second equation with the second equation minus the first equation. 3x minus 3x is 0x's, and 6y's minus 0y's, that's 6y's, is equal to, and I've got 9 minus negative 6. That is 15. Alright, and the first equation I leave as is. 3x plus 0y is equal to negative 6. And you probably think I'm crazy for keeping around a 0y and a 0x, but it's kind of a placeholder so that everything lines up, that the get out of your hand, so that the y's are lined up and the x's are lined up. Okay, So originally my goal, starting here, was to simplify the system of equations to an equivalent system of equations, which is simpler. Certainly I'm there, but there's one more simplification, well, two more simplifications I can make. X is negative 3, and y is, let's see, 15. Oh, yeah, okay, so 15 divided by 3 would leave me with 5, and then I have to divide by 2 again, 5 halves. Okay. Oh, you know what? I see I made a mistake. Back here, you probably caught this before I did. I subtracted the second equation from the first, and I should have subtracted from negative 6, 3 to get a negative 9. How can I fix that? Negative 9, like that. Okay. Negative 9, and that should have been a negative 9 over here since all I did was copy the equation. But to obtain that equation right there, I took 9 minus negative 6, and that should have been a negative 9. 9 minus negative 9 is not 15, it's 18. Okay, so fixing that, I've got 18. 18 divided by 6 was 3. Okay, so 3. All right, now that's a nice simplified system of equations. The only solution to this is the point negative 3, 3. Okay, so O-N-L-Y. Oh boy. O-N-L-Y. The only solution is negative 3, 3. And I have not yet found the local extrema, because while I know that there is a local extrema here of some kind, well, rather there's a critical point here, I don't know whether this is a local maximum, a local minimum, or something else, possibly a saddle point of this function. So let's see which it is. First of all, we want to look at a certain second derivative of this function, since this is a nice place to use this notation, fxx, the second derivative with respect to x. Evaluated at the point negative 3, 3. Let's see, what is the second derivative with respect to x? The first derivative with respect to x was this, and so the next derivative would be 2. Okay, and that's greater than 0. And the discriminant is fxx, the second derivative with respect to x, the second derivative with respect to y, and you subtract the mixed derivative fxy squared. And this right here, the product of the concavity in the x direction, the concavity in the y direction, this term right here measures if the concavity is the same. Right? Concave up means this will be positive, and concave up in the y direction means this will be positive, and then the product will be positive. So if the concavities are the same, then this term will be the same. And we need to evaluate that, of course, at the point negative 3, 3. Okay, so let's see. fxx, we just calculated that. That's 2. And fyy is also 2. fxy, let's see, that is the derivative with respect to y of this derivative with respect to x, so that is a 1. Minus 1 squared. So I need to evaluate that at negative 3, 3, but it's just a constant. It is, let's see, 4 minus 1 is 3. That's greater than 0 also. So that means the concavities here, fxx and ffy, the concavity in the x direction and the concavity in the y direction are the same. And apparently they're both positive because the concavity in the x direction is positive. This term right here comes from the existence of cross terms, of course, and it only occasionally plays a role. Okay, so since we have concave up in the x direction and the same concavity in both the x and y directions, and this correction term is not ruining that, we can say f is, well, think about it. F is concave up in both directions at negative 3, 3. So a minimum, I should say local minimum, of f. And the value of the function there is, oh, let's see here, negative 3 squared, that's 9, plus 3 times 3 is 9. Oh, with a negative sign, though. Oh, cool, so those will cancel each other. Plus 3 squared is 9. Plus 3 times x is negative 9. Oh, man, this feels ridiculous. Minus 3 times y is 9. Plus 4. Okay, so this guy and this guy are eliminating each other. This guy and this guy are eliminating each other. I still have a minus 9 and a plus 4, and that is negative 5. Okay. Now, that is a local minimum. Is it the global minimum? Is it the smallest that this function ever gets? Well, we need to check the boundary of the domain of f. Okay, the boundary is all of R2, all pairs of numbers. There's no restriction that comes from this. Is set without boundary. Okay, there are no other critical points. There are no other places where we possibly could have a maximum or minimum. This is the not local minimum, but actually minimum. Okay, so to recap, in order to find the local extrema and global extrema of a function, what you need to do is find the critical points. There are two kinds of critical points. There are places where the derivatives are equal to 0, and then there are boundaries of the domain. There are also discontinuities, but there are no discontinuities for this function, points at which discontinuities occur. So I'm checking all of these critical points. The critical points only, in this case, only come from the places where the derivatives are equal to 0. I showed you a method of putting together equations where you simplify the system of equations to something where it's really easy to read off the solutions. And then the second derivative test right here tells you if you have a local minimum or a local maximum. You then have to compare the value of the function at those local minima and local maximums to the value of the function at all other critical points, but there weren't any other critical points. So I found the minimum.